this to get some surfaces get heat up very, very quickly, which is quite unfortunate. So we have went through version 1 and version 2. There is actually a healthy improvement. And what we learned is that we need finer control on quite a few things. There are 5 total problems. The first is a nozzle overheating. Second is the substrate is too hot. Third is the spacing between different parts are not accurately controlled. There are limited repeatability between experiments. The fourth one currently we didn't implement a printer. So each of them, we did some engineering control to ensure that it's going to hope that it's going to work better in the next iteration, version 3. And our target for version 3 is that we want to achieve repeatable, controllable, porous metal nanoparticle film printed on selected substrate. And in the future, if the throughput is decent, we are able to, I think we can scale up for loose nanoparticle production with an additional cold trap to collect the nanoparticles. So actually this morning, the reason I'm like on the grab is quite stupid. So we bought the wrong 3D printer. So Ali was suggesting we need to buy an Endo 3 3D printer, and I sent it to ANR like 2 months ago. And currently what's available is Ender 3v3, which uses totally another layout, which doesn't really work well for us. So there's no option, no new version 2, which is the one we are comfortable with. So I have to search on Carousel, find a seller, and who are only able to deal like either like 7 a.m. or 10 p.m. at the time I'm choosing. So I just went to Samba One and grab this back to create. The setup is actually pretty straightforward. If you look at the layout, there are 3 actually main parts. Basically, this provides all the power and information, so signal feedback from the temperature sensor and current. So it's able to help us control the temperature more precisely at required timescale. So we had a hardware PID board already. We also have like a not clearly just a common DC power source or already board. We have 3 temperature sensors, each of them governing one of the surface, and it's the IR number 2. Sorry, I typed wrong. It's governing the carbon heater. We have another 2 assemblies experimentally. The first one is the reaction assembly, which is a combination of ultrasonication nozzle plus the carbon field heater mounted on the Ender 3 head. So because we mount them together, the spacing, the one between the carbon filament and the ultrasonication nozzle, we think we can control them more precisely. And the D2 is the space on the printing assembly. The printing water cooling base plus 360 millimeter heat dissipation fan mounted on the base. So with this, we're able to definitely control the temperature on the surface pretty nicely. So this is the control for the heater and for the substrate. And for the ultrasonication, also it also gets heating very quickly. There's no good ways I'm able to think about. So the only way I was thinking is I can change the cooling gas from argon to helium because helium is lighter and the thermal conductivity is higher. There's nothing else I'm able to think about it. So that's all about it. It's going to take us a bit of time to put things together. There are like quite some parts we need to 3D print and maybe experiment a bit. So that's the end of the presentation. I think if any advice or any questions, please ask.
Okay, so I can start with a couple. So I mean, I have two things that come to my mind. One is, for this design, is there a reason to only stick to carbon paper as a heater? Because
okay. Yeah.
Yeah, like the reason we use carbon paper as cover thermal shock is because the thermal conductivity is very high, and so
Yes.
it's fast heat dissipation. You don't need that
Yes.
property here, right?
It depends. We can buy some coils, like the typical heating coils in the furnace. The only issue for that is it doesn't heat up that quickly. So the moment we want to stop, we have some issues. We cannot stop. So we did bought some coils, but we need to give a try. Currently, of course, if we want to ramp up to a target temperature, say within 1 second, and control it, if the current need to adjust with the fastest response, carbon is the best option. But if a heating coil, the response time is probably like in minuscule.
Right. I understand. The second is you should do some background IP search. Okay, you're building this from scratch.
Yes.
What exists in aerosol printing? What exactly is the differentiator? Since you guys
makes sense. Yes.
Before you do anything, check for prior art.
Yeah.
Okay. Sometimes it seems obvious, but what might happen is that there's somebody either solved it in a patent or
solved it in a patent. Yes.
And I'm also assuming that when you do something like this, there will be something that can be filed as IP. So if you start,
or maybe I'm infringing somebody else's IP.
Yeah, which is okay if you only use it for your own research purpose, right? So that's fine. But I mean, every IP has extra work on it, so you can build on something. You have a translation stage, all that stuff adds to it anyway. But just make sure that maybe someone's already solved it, and second, what exactly is. And always remember the goal, okay? Because once you start on a project, like it becomes a sub project. You want to make catalyst material. So anything else that's not in service of doing that, not something you want to prioritize. You probably can do a lot of other things. But your goal has to be very, very clear. There has to be aerosol mixing of pure particles, and there has to be in situ annealing. An old problem that we've been trying to solve for a long time. So with Ali on board, I think you can definitely do it. Which means once you start building this, think about the characterization that you need. Okay, at the I think you know all the tools, but what really proves that there's actually miscibility and all the stuff that you did in your paper before, and what is the simplest way to prove it? I think even XRD might be enough, right? Because we're seeing that it works for the other catalyst materials quite nicely. For the DJS-based synthesis. So just keep these things in mind and only focus on that problem. Okay, later we can expand, but let's solve the actual problem here.
It makes sense. Yes.
I'm quite positive because Ali is quite good at making stuff. So he has a design process and a manufacturing process, everything. So I think he should be okay as long as he has time to do it. He's working on 3 projects right now.
Yeah.
Cool. Any other comments? No.
And then I'll just stop sharing.
Shall we go to the catalyst synthesis stuff? Because I think we haven't caught up for a while. I think, Mahesh, you mentioned that you wanted to share something, right? At some point.
I think he is in train, seems like. So he'll present next time.
Oh, okay. All right.
But I have something to present if I get that time.
Okay, so after I think we'll go to the catalyst synthesis project because
sure.
It's ongoing right now. So if there's anything feedback, I think Christine and Delvin are working on it. So maybe Pepe, you wanna present it and take it away?
Yeah, I do actually. I was going to show you guys my photocatalyst data, photoelectrocatalyst data, because it looks pretty good, but I have something better actually. I think this is pretty self-explanatory, but I'm gonna go through it.
Oh, phase viewer all the way.
Yeah, not really actually. This is really interesting. I just got this data yesterday, so I've only spent very little amount of time analyzing the data, but like basically I can now do in situ XRD here in nitrogen, and the results are fantastic, quite frankly. I tried with like this sample because I had it handy and it's not so important. So basically, it starts with, as we know, silver antimony telluride. Then it goes, and we have some silver telluride as well. And as temperature increases, you notice that this peak appears, and these little peaks also appear, right? And it's quite nice because you can correlate that. I have data. The granularity of this data is 5 degrees per step, so I have data every 5 degrees. The ramping rate was 5 degrees per minute, and I held for 10 seconds per scan. And for those of you that might be concerned that I'm not scanning for long enough time, just a quick reminder that for you to be able to do Rydberg refinement on a material, your most intense peak should have a factor of 1,000 counts over your background. And that happens here. So it's pretty good.
Is it AG2T or AG5T3? What is that?
It's specifically AG4.66T3.
I thought you have AG2T issue.
I mean, AG2T is a very interesting compound, and I can send you a number of papers that you can read upon. But basically, the phase diagram is very complex, and non-equilibrium synthesis has a very big... Equilibrium synthesis has a very big impact on it. Non-equilibrium synthesis even more. And I'm glad that you raised that point, because as you raise the temperature, what happens is that you start seeing the composition of a silver antimony telluride. Most surprisingly, it decomposes into antimony telluride first. And I know that because the phase fraction of antimony telluride increases with temperature, right? So here's the pattern at 250. There is much more antimony telluride. And when you get to the maximum temperature of the scan, which I set to 350 because that's what we have in the paper, essentially, it's completely decomposed into antimony telluride, and we have this like silver telluride appear as well. So it's not very surprising data, but you can imagine applying these to other compounds, doing this in situ at different like ramping rates and so forth. We cannot control the cooling rate very well at the moment. Yeah, go on.
So you get the percent by intensity ratio, 33,
no,
30.
It's Rydberg refinement. The way it works is a little bit complicated, but the intensity is involved, yes.
Okay.
And we've been doing this in the group for a couple of years now, by the way. So you should have seen these graphs before. So yeah, so I just want to show that, you know, like we can sort of like have an understanding of how phases decompose or behave at high temperature. And we could do this with varying ramping rates, which is anyway a project I'm involved here with Gerd. And we could, as a matter of fact, map these back to synthesis. So I was thinking that, imagine that we had a phase that we were interested at this temperature, then we could do Joule synthesis at that temperature, quench it really fast, try to stabilize it at room temperature, and so on and so forth. So in the space of the next days, I am hoping to be able to get more access to the machine, because a new postdoc joined the group, and his project is to automate the in situ XRD to integrate it with the A-lab, which is not as easy as it sounds, by the way. So I don't get access all the time, but you know, we work together. So I have time tomorrow. So tomorrow I'll be measuring more silver antimony samples. And yeah, so essentially, if you guys want any in situ done, please send me the samples. I will find time to measure for you.
Can you
And
go
I
back
think
to the data? Like,
Yeah.
I just want to see our
Yeah.
max temperature was 575 Kelvin for thermoelectrics.
But we could go higher in temperature, Kedar. I did not, because first of all, because I don't want to melt the compound because that would damage the chamber. And also because, quite frankly, like this is as much thermoelectric data we have. So I thought it would be good, but I'm happy to repeat the measurements to higher temperatures if you want.
No, but so yeah, what I'm thinking is,
Yeah.
So 575 Kelvin is how many Celsius?
350?
Is 350. Okay. And what we should try and do is, there's a peak. We see the peak that drops, right, in the thermoelectric transport.
Yes.
Just to correlate what you see for different doping with respect to this.
Actually, yes, Kedar, you're absolutely correct. Let me share my screen better. Sorry. Okay. I just wanted to show you how the data looks like, right? Like, so this is how it looks like. So I have data for every 5 degrees. We could increase or decrease the granularity.
Yeah.
And I am sorry.
We don't need to increase the granularity, I guess, unless something changes with the way, if the heating is done faster or slower, if the phase evolution changes. But the ramp rate should match what you did with thermoelectric transport in a way, right?
I did that, yes.
Yeah. So if that's the case, then what we have is some nice evidence where we can correlate this, and let's see hopefully it goes out for review. And, if it's out for review, let's see what the reviewers come back with.
Yeah.
If not, just be careful of the choice of samples. What I mean, like, I think we could actually use this data for is Cheng-Wang online. Cheng-Wang is not online.
Yes, I'm online.
Okay.
Definitely online.
I was like, you didn't. Okay, so for your synthesis paper, right, Cheng-Wang, this might be a really nice addition.
Yep.
All right.
Well, that's a shame because I was working on something else, but if you want me to give this data, I'm happy to do so.
Sorry?
I was working on something else that I was planning to use this data, but if you want me to give it to Cheng-Wang, I will. So let me know.
No, if you want, I don't know. What do you want to use it for?
Oh, I was working on like a nice paper explaining like how the non-equilibrium synthesis affects the different decomposition.
That's fine. I mean, you discuss it with Cheng-Wang.
No. I mean, if he's doing it, like, I don't want to, I have way too many things to do. I'm more than happy to give him the data, I guess
I don't know what you're saying. So anyway, the point is that if you have something that you're working on, which is separate, you figure it out. I guess the reason you're presenting is I thought that you can add this paper. It's up to you to see if it's worth it or not.
Absolutely, yeah. So I'll measure all the samples he sent me and I'll send the data for sure.
Or if there is other things that you can do with it, then please go ahead. I mean, it's up to you to use the tool. It's your tool in a way.
It's not mine, but yeah.
Okay.
Yeah. So also I in a quick one-liner, I can tell you that so we made a mistake before with the photoelectrocatalyst and we did not prepare the correct composition, which explains the funky XRD quite honestly. Nonetheless, we got a 25% conversion, which is not great, but for a compound that shouldn't have been made in the first place is not too shabby.
Mm-hmm.
I've also recently learned that we can get away with having larger particle sizes. So things that are 1 micron or slightly below 1 micron are okay, which can open a lot of possibilities for you guys as well, if you want to make this compound. So I spoke with Christine a few weeks ago, I think it was, I don't remember. And the data looks good. So we're gonna, Christine, I will follow up with you at some point this week. So we're gonna make a few more samples, send them here.
Yep.
And then we will go through the testing again. And when that's done, hopefully I can give you more insights about what it requires to design and measure properly photoelectrocatalyst, because we can make them. They are mostly sulfides, which I have a lot of experience on during my PhD, and we've been reasonably successful with only like 2 attempts.
Okay.
Yeah, and also very quickly, and I'll shut up. Kedar Uting is having a lot of difficulties accessing the XRD, and we are getting some really nice aluminum doped germanium telluride that one verifies, can be used to verify Andres' ZT curve prediction. So that project is like reaching the end of its natural life. We are doing some validation to be like, look, our model is this good with respect to the measurements. But also we will be using this data for the germanium telluride project. To the best of my knowledge, there is no data of aluminum doped high entropy germanium telluride. So we can do this. And aluminum, as you probably know, is an amphoteric dopant in lead telluride, a material that it's quote unquote fairly similar to germanium telluride, structurally and also in terms of band structure. So I think it could be quite interesting to investigate that. So if you could please like get down to facts in person, I know it's a lot of work, but like if you could go there and be like, hey, why are you not giving access to my people?
So what's the status in the XRD?
You think, do you want to comment? Or Chengguang, I think can also comment. So I'll let them do the talking now.
Okay, so
yeah.
okay, yeah, you
Go
okay,
ahead. Go ahead, yeah.
yeah. So for XRD, I think Willing mentioned that he did not want to give us the access due to the large number of incidents, which is not our cause, I think. And for XRD, so basically, I want to like access the office hour because it's very crowded during the daytime, and I can because our scanning time is like 1 or 2 hours for one sample. So it took a long time to scan one sample, and we likely got a few more samples that we want to see the XRD results. So I think it will be better if we got the office hour access. Yes.
Okay. Chengwang, can you send him an email and CC me? I will be on campus on Friday. So let's try to meet up with him Friday. Let's talk to him and see what he says.
Okay. Yeah, I think there are several new instruments imported into the FACS, but unfortunately we cannot use it because all our previous experiments are based on the I couldn't really remember the brand of the XRD. Yeah, but right now it's changed to a new brand. So for each of the instruments, since like the goniometer radius and even the beam intensity is very different. I mean, the beam source is very different. So it's better to keep the same instrument to measure our sample. I mean, at least we need to finish this project by using the same instrument. Right?
I disagree. That doesn't matter if you do refinement, because when you do refinement, the instrument parameter accounts for it. So you are already correcting on it. You don't have to use the same instrument.
But the cascade plot will seem a little bit different.
It's a plotting problem, not an instrumental problem then, right?
Yeah, I mean, the plotting problem comes from the different instruments. Yeah, but I mean, if you only do the refinement, then it's okay.
I mean,
okay, man, your circus, your monkeys. Okay.
What exactly is the problem? Because it should not depend on the instrument, right? What do you mean that you need to do the samples on the same instrument? Can you explain?
It's just previously I tried both the D2 phase and then the DAA. Then I got. I mean,
Hi, Chengguang. So there's one thing. So I think if you use the D2 phaser with with a default 0.6 millimeter slit, it's going to give you much wider peaks and slightly different peak shapes. But I think if you use Rigaku one, it's going to give you similar shapes, and I don't think people is able to see it. The default settings for the Rigaku one we have is similar to the Brooker DAS.
Okay, I see. Then problem.
But if you are still very picky on this, then what I can suggest is with a series of samples, you just use one XRD, and between different series of samples, you can use different tools. I don't think it's a big trouble.
Okay.
Depends on what you want out of it, right, Chengguang? What do you use XRD for in this project?
Mainly for the refinement, actually. But I mean, probably just because I use a wrong machine, right? Like HiWinZ, like D2 phase and the DAA are quite different. So, but I did experiment in those instruments. So I was a little bit worried about this.
Cheng-Wang, I built a Topaz model for silver antimony telluride when I was still in Singapore. So you can use that to refine. The model is built. You just need to switch the data and click refine.
Okay.
And if it misbehaves, which is possible because Topaz is a really bad software, send me the data. I'll do the refinement for you, and I'll send you back the data, and you can do what you want. But like, I don't want you to get stopped because of that.
Yeah. Right now, my problem is that I didn't. I mean, we didn't promise that if I submit the report, right, and they will give me the test, and then I will my access to the XRD will be retrieved. But right now, it didn't happen.
Okay. So
there's no response from them, so I still have no access to the XRD.
I hear two things. One is that firstly, you think needs after-hour access, right? And which XRD do you need it on? Is it the new tools or the old ones?
The old one.
Okay.
I think for the new one, I have no idea about the new ones.
Okay, so there's a few things to do here. Right? One is to get back in his good books. Okay, this happens sometimes. Okay, you have to really show that you care, and you really have to care. Okay, you need the tool. This is normal. Okay, you have to show them that you're putting the effort. Start from scratch, whatever it takes, get it done. Okay, we're going to be here for a while and need that tool for your project. So there's no shortcut around this. Okay, unfortunately. So what we have to do is like basically talk to them, say, oh, look, things happen. Let's clear. Let's start from scratch. We'll do as what should be done properly. Let's get you back access, and let's ask for you things after our access. And we'll tell them that I think Jayant, are you using the XRD, right? So is Delvin. And is there a problem that there's too many users from our group, or is that not a problem? Sorry? You have more daytime and night access, after hour access. My feeling is
I do not have.
For you think it should be, sorry, Delvin, one second. For you think it should just be because she's not a PhD student yet. So they don't give you priority, you think, but we will talk to them. Tell them that, you're trying to come in January as an incoming student. Sorry, Delvin?
I do not have access to after hours XRD.
Okay. Do you want to have access to after hours? Or?
Sure. Yeah.
Okay. So I will check that. Let's find out what the problem is. I don't really know what the issue is here. And then we will see. So Jayanta, for your time, are you able to get easy time after hours? Do you have, if you want to do XRD in the group? So I don't think you should be limited by this. Clearly, Jayanta has access. Maybe even Ivan, you have after hours access?
I never have any problem with XRD. I have every access.
Yeah, so this is not an issue. You should just give it to these people to do the XRD for you, okay? For now, at least, until we sort this out. So from what I hear, this guy, what is his name? Whatever his name is, Alan, right? He has a problem with you, Cheng-Wang, and because you think works with you, you see he has a problem with her. This is my situation, but let's talk to him and find out what's going on. It's okay. Let's just sort it out.
Yeah.
All right. So Friday, maybe you think should write the email. You think just write the email and CC me and say, hey, don't write much. Just say it'll be just to understand say something like just to understand the limitations of XRD. It would be just nice to have a chat, and that Kedar will join the meeting if possible to discuss access to the XRD. Just say something simple. Don't write anything. Okay.
Okay.
All right. Okay. Thanks for bringing that up. Since I'm an associate manager, I can manage this. Anyway, so what about the catalysis thing? Is it going well? The synthesis, I saw Christine. I think thanks for the nice updates. Delvin, thanks for the nice updates. Anything you guys want to bring up with the synthesis? Is it progressing as expected? No issues so far?
Yeah, no issues so far. We've been doing it pretty fast. So I think in a day, we could synthesize like maybe like 8 sets of samples. So that's 24 synthesis in a day.
Amazing.
And then we do XRD in the afternoon. But we've been just bottlenecked by the XRD. Yeah, because we could only book like 4 hours at one time. And yeah, but so far so good. Yeah.
Yeah, so you can use, if you want to, you can use Jayanta or Ivan if they have time, right? You could just ask them to do after hours. If Christine doesn't have access after, they can help you. If you bottleneck with XRD. But seems like it's not a real bottleneck. So in a way, it's not bad because the IC squared guys also have to be ready with their testing, right? So
exactly, yeah.
I don't think you have an issue.
Can I say a couple of things to this effect, by the way?
Yeah.
So one is that the data looks really good. So the point of contention is a minority nitrate phase that forms, but it's always below 5%. So please ignore it.
But I was wondering about that because like it could have an effect, right? Because the nitrate is coming from the dopant, from the activator.
Yes, from the sodium nitrate, yes.
So that would be an issue, wouldn't it? Because doesn't that mean that you don't have the right amount of sodium inside the matrix?
No, the nitrate is a metal nitrate. So like, zinc nitrate or zinc iron nitrate or something like this, right? It's not, let me, you're right. Let me quickly go and check the data that I refined.
I'm curious what happens.
Yeah, so
it's not supposed to be nitrogen, pure metal phases.
Can I share my screen real quick?
Yeah.
Thanks. So this is an example. The nitrate phases are always metallic, and they are always like about 5%. So as a rule of thumb, like 5%. Sorry, go on.
What is ZnFe3n?
Yes.
Fe12n5?
Yes, these two. And
nitrides.
Yes.
They're nitrides that are forming.
Yes.
Okay.
So this has been reported in a paper, which is where I read it and found the phases. It happens when you react nitrides and you do self-combustion. We are not doing combustion, but like we're still applying high temperature and doing like annealing. And again, these phases are always present in like 5% or less. And as a general, I tend not to trust or to be skeptic of like phases that are like around 5% in Rietveld refinement. So they may or may not be there. So it matches the peaks and it matches the literature. However, I read the paper, which I'm happy to send again if you want to take a look. And it seems to be not that important. They don't discuss it in detail, but to your point, the promoter is not in these compounds. So all the sodium that we have is sodium oxide, which is what it should be. Maybe not high crystallinity, maybe it's too low to detect it through XRD, but the promoter is not in the, shall we call it, impurity phases.
Okay, so firstly, when you said it's in literature, is it in the benchmark paper that we're talking about or not in that one?
Not in that one, it's in another one. Because the benchmark paper that we are comparing did sol gel synthesis, so they did not burn the precursor, they burned the gel. So the gel is an oxy something, right? It's not an oxide, it's an oxy something. The paper I'm referring to that I found, they were using self-combustion of the precursors directly. So it's more akin to what we are doing in our synthesis.
Okay, but so because the performance might come from a few effects, right? The iron has a role to play, cobalt or zinc has. So if you have smaller percentage of each of those metals with the impurity phase, how does that affect the performance? And how does it compare to the first synthesis? Because I don't remember this nitride phase being there in the earlier synthesis we did, which is what Andre used for the optimization run.
So I'm going to answer your questions in the order that you have asked them. First of all, yes, you are correct. However, I would be a bit more worried about quantifying amounts of metals and semi-metals or whatever in the surface. So XPS. We should look into the XPS data because I think it might be able to help us explain the performance better than the bulk composition, which is what comes from XRD. XRD does not give you composition, by the way. XRD matches crystallites to faces in a database. I'm happy to do the SCM EDS here in Berkeley because we have the auto SCM software, and it will give us better composition. But again, it will still be bulk composition. But you are correct in the sense that this could affect the performance, and I don't have an answer for that at the moment. But also that's because I don't have all the data. Now to your second question, why is it not similar to the same synthesis? Because initially the amount of nitrates were very low. At the moment we are putting more. So we were sticking to that 90-10-5, 90-10-5, 90-10-5. So I would say, I could be wrong, you know, I could be wrong, but I would say that that's the reason. Now the compositions have changed and therefore what we get is different.
Now that you've found these nitrate fields, can you go back to the old XRD to see if maybe these peaks appear anyway?
I did, they are not there.
They're not.
But again, from our AST work, we have learned that the fact that they don't appear in XRD doesn't mean that they are not there.
Yeah, of course.
So they could be there, maybe present as an amorphous phase like the sodium oxide. Again, we've never seen sodium oxide in our peaks. Why? Because the concentration is low and perhaps it's not super crystalline. XRD is only good at that, and we know this because of the AST paper, right? XRD is only good at detecting things that are 100 nanometer or above. When things get below that number, things get funky. And we've seen this in our thermoelectric work. So I could be wrong, you know, but I'm not super concerned about this. I'm actually more happy that we found the impurities and they don't come from ICSE squared or they don't come from other sources, that they come from our own. Yeah.
Okay.
And sorry, please. No, I just wanted to say another thing. So
yeah, go ahead.
If I haven't answered your questions, please ask me now because I can clarify.
No, I mean, it seems to me that as a part of our synthesis, when you change the composition, it's possible nitrate phases are being formed.
Yes.
That's the conclusion.
So I would like to say that like today, the catalysis ETH, the SwissCat people have visited, and I was around, so I got to meet the guy, and he said that he'd be happy to collaborate. They have pretty nice facilities. So Kedar, to your point of like, it's good that our synthesis is taking longer because we are limited by reactor time. This could open avenues for collaboration for you specifically. I don't know if you want or if you don't, but I'm just telling you so you know.
I'm aware. Was it? Okay. Pavel Level something, French name?
Yeah, French
Pascal
name.
Level.
His name is Paco, which is a Spanish name, but his surname is French, so it was very funny.
The reactor is not as good as the HT.
Okay.
So the HT is actually better.
Okay.
I checked this. I visited them last year.
Oh, okay.
So I've met them, and actually Javier has better reactors than they do. But they're trying to automate it and stuff. Still early days.
Okay.
I think HT is better, so we're working with HT guys.
Okay. I just wanted to tell you because I thought it was relevant.
Sure, thanks. I mean, the one thing to do, right, but please make sure you drive this project, keep a close eye and close watch because this is your paper, right? So
I am.
Yeah.
I am.
This is a really critical one, so please drive make sure everything is done. This is the one project that I asked that you do that because I think we need to finish that, right? This is going to be the last run. I think unless we're getting closer, the Pareto front is moving. I don't anticipate many more runs. Maybe one quick one after this.
Yes.
Right, Delvin, Christine, because Andre's already been very careful with everything here. We chose the chemical space very carefully, and there's a nice story building, and hopefully the results are in our favor. And then maybe one more round, and then that's it. Whatever the results are, we write it up.
Yeah.
So this is basically the last piece. So please keep a close watch on this, and I think you would even start writing the paper and discussing the narrative, right? I think it's very important to do that.
So yes, you're right. And you were not present in our meeting last week, but like basically the problems that have arisen is because of my lack of oversight, and that's on me, and I apologize. That being said, I'm in much more regular contact with Delwyn and Christine and Somia. So we have a group chat where we discuss like daily kind of like run of the mill things that are not super important, but like they are relevant for the progress.
Yeah,
so
every small thing is important.
Yeah, and to that effect, I would like to say that we're in very good shapes. Christine and Delwyn and Somia are doing a phenomenal job, much better than me, quite frankly, at the moment. So we're good. And yes, and also I already spoke with Amol about the paper, and I started drafting the figures.
Okay.
And I've been not very actively, to be honest, but I've been doing that as well.
Great. So let's hope. I mean, also us next week when we have the meeting. I think that we're going to have a meeting with them next week, right?
We have a meeting this week.
Oh, we have this week. Okay, great. So we'll sort it out when they have the reactor time, and we can sort everything out. Christine has been good coming back. Everything's smooth after your return.
I think so. Yeah, I think we can finish first 14 by next week, hopefully. Measuring everything.
And this is your primary work, like you're basically focused on the catalyst materials, right?
Yeah.
All right, doing other synthesis too. Are you doing any other materials apart from this?
Any other materials? Yeah, I'm doing the copper, silver.
Copper in fine. Okay. Yeah, maybe we can present a couple of present yourself today in the group meeting if you want. Yeah, up to you. I think there's a lot of people who might not know that you're going to be in the group for a year at least. So just introduce yourself so everyone knows, if that's okay. Christine, is that okay?
Maybe I will prepare and do it next meeting.
Yeah, that's fine. No problem. Okay. Sounds good. So I think we'll chat more in detail on Thursday. So I already spoke with Jayanta. So I don't want to, unless you guys want to hear what he's doing. I think he's solved the mystery of the low temperature phase. He's working on the paper at this point. Maybe he's already touched base with you guys. So and he's working on both of his papers now. And it's a bit urgent to make sure the paper goes out. So Pawan, Mahesh, I think he sent you the draft of the paper, right? Please take a look. If we can sort of do some simple calculations based on existing band structure to explain the transport, that'll be nice. The only thing I asked Jayanta to do extra is I think that copper vacancies will definitely play a role in the doping. So for the copper titanium telluride, he is definitely overdoped. And copper vacancies are going to cause p-doping, right? So 10 to the power 21. So if we try to add excess copper, I asked him to do both excess and less copper. And so, if we show, it's an easy experiment because you don't need to introduce an extra dopant, check solubility, other phases forming, all that won't happen. So just add extra copper and reduce some copper. I think this is the only experiment I asked him to do because I think it's important to push that paper out. And I think, Jayanta, as soon as Andy's back, I don't know when, I think he said end of the month, right? So as soon as he's back, send him an email and let me know. Let's sit down together and let's make the task very clear for him. Okay, so that you're not bottlenecked by that. Right? I think those are the last two steps that he needs to do. So, Pawan, like if you can help with the transport calculations, if it's overdoped.
Yeah, I am doing. Yep, I'll finish. I'm just waiting the input, then I'll work it. I will explain all the transport.
Even the band structure?
Not band structure, thermoelectric transport, I will explain.
Okay. Well, I mean, he has the data for the SPS samples. Not the one. Mahesh, man, we're limited by the SPS, man.
There's some issue with SPS. It's solved. It's like 2 months down, then it's solved. Again, there's another issue. So this is like not, it's like only tuning the knobs. So he's coming on Thursday afternoon. Even I'm eagerly waiting for my samples as well. Yeah.
Can you block access after this to anybody else?
This issue also gone again came along with the lady, same lady.
Yeah, so just tell Shijay. I will tell him like right now we're having a lot of issues.
I cannot blame, but it may automatically came inside or from the user. I don't know.
No, it doesn't matter, right?
Yeah, we can ask to train another user from the group.
No. Just start with saying, for now, we want to make sure this machine is stable.
Yeah.
So it's not, she can give you the samples.
Yeah.
Do it, right? Just help them out. They're also on Mad GDT, by the way. Okay.
Yeah, I know.
So they're on the same project. And so tell them, like, give us 1 or 2 priority. Of course, we don't want to hold back anybody's work, right? But tell them, like, this is because everybody's project, including yours, is held up. And I said this, tell him, like, I don't think you need to have the SPS working and robust. And so they do very high temperature, right? If that's what it is.
Yeah, true.
That's the problem.
Yeah.
Okay, and when, of course, you go very high temperature, you're at the limits of your machine, things are going to break. It's not a surprise, actually.
Yeah, fortunately it's not electronics. It's like not electronics components. It's like the piston. I'm also going to do some maintenance with the vendor only.
But I mean, how long will it take though? That's the question.
No, this Thursday afternoon we are going to check. But this is sales guy. It's like the communication is very bad. You cannot communicate with a Japanese guy, and he's the slowest person I ever seen. So he mentioned, don't contact me directly through salespersons. Yeah, very bad communication. Right now, Thursday afternoon is coming and going to check some tuning knobs. Hopefully, we'll fix.
Okay.
Yeah.
Chengwang, you get a quote for the SPS, man. I know I said I don't want it for a high throughput. We had a long discussion, but you give me the quotes anyway, okay?
Okay.
This is just seriously is not fun. I mean,
okay, of course, yeah.
Yeah, I mean, I think germanium telluride samples will be blocked.
And the copper telluride mine also.
The copper telluride samples, the whole work that needs to happen. And I think there's going to be more. I think the new compound we haven't even tried yet with the copper germanium telluride. So and your own samples. And then there might be a whole thermoelectric effort afterwards, which is going to be machine learning driven. So, it's just, this is not fun. But I don't know. Maybe it's an old machine also, right? We've had it for more than 10 years.
No, it's like, it didn't get any repair so far. Like only 1-2 times is broken. Only one is quite robust. I could say.
I mean, the other thing that's happening is Raju will probably retire.
And that SPS is but different.
Good, right? But he doesn't
compared to that SPS, PS, this system is much robust.
Okay.
Yeah, but the service is bad. Yeah.
Okay.
Yeah. This like I don't have
the main issue with adding and removing copper in Jayanta is that there's no way to know if you de-doped, right? Or doped, unless you do SPS.
Yeah.
The idea we need, like, is there an optical probe, UV, something that can tell doping, de-doping?
No. What you can do, you can prepare the samples by DGS. The strategy, whether it is SPS or DGS, strategy will be okay. So previously he's getting
You just do a simple measurement without high transport property.
I think you can do the UVBS also.
Yeah, I think it's a good idea to try optical. We'll learn something about it as well.
Yeah, I am actually, that's my idea talk maybe next time.
Okay.
But there is silicon people using absorption spectroscopy. The intensity in the sub-band gap tells you how much doping you have. Yeah, there is some paper there for silicon itself.
I mean, but this is a very small band gap material. This is 0.4 EV.
Yeah, so you need to do FTIR.
Yeah.
Below band gap, if you see any intensity or any absorption, yes, there will be.
We don't even know if it's 0.4, by the way. This is not a very high level of DFT.
So, yeah, I think he already ordered the KBR pellets, so we can try.
Okay. Yeah, but I mean, the handheld CBAC even might be an easy way to do it.
Yeah, it's easy also. CBAC also will tell you.
Jayanta, your CBAC is not sensitive to geometry.
Yes.
So as soon as you put in any sort of dopant or de-dopant,
yes, CBAC will tell you.
I agree with Mahesh. Just to sample, take any surface and just measure the CBAC Pawan has a CVAC meter.
Yes, handle me, yeah.
And then just use the CTA. Okay, even if you take the smallest sample possible, I think Chengmong knows how to do this. It might not be ideal transport, there might be some porosity and stuff, but for the trend, that's sufficient.
Yeah, I can help.
Yeah, he can help with it.
Is CTA back? Is what the issue with the CTA?
CTA, okay. There was some air conditioning maintenance in the clean room, right? So some people, if they use the machine and they shake, the machine was shaking, and so on the main board, actually the connection loose. So the PC cannot receive the communication from the communication was not very good from the CTA to the PC. So even though everything works well and works normal, but there are some issues showed in the software that there's no water flow or cannot apply the heat gradient or something like that.
Is it solved?
Yes, solved.
Cool. I mean, I don't have experimental results, but the idea on zirconium selenide, just waiting, every sample are ready. Just need to, the vacuum sealing issue, then a vacuum sealing issue is solved. We are not going to buy the full off of the equipment. We bought another adapter, which is little different, but we able to fix it. So one I bought 700, 750. Then I'm going to buy 2 more adapters. So no need to buy the whole machine. Yeah. Only this SPS now and furnace. Yeah. Can I present the idea?
I mean, up to you and Pawan. I have a hard stop at 10:45 because I have a meeting at 11.
Yeah, mine is simple, small. Let me share. This is I shared before, but a few more details. Sorry. Can you see my screen?
Yeah.
Sorry. This is interesting system which we found from the FIP project as well, and this is a layered material. People been studied on 2D like monolayer and few layers. This is like a zirconium selenide, and then we are interested in tuning the band gap, then tailoring one of the dopant at the anion site. What is interesting here is a zirconium selenide is like a hexagonal structure with a band gap is more band gap like semiconductor. It's not like wider. It's like a 0.7 EV, 0.5, where you can able to tune the band gap with tellurine. Particularly, you can tune few percentage of tellurine, and then with the percentage of 50 is kind of Janus material. The Janus material is nothing but each one layer is corresponding to Te, another layer is selenium. So it's perfect semi-metal, even at the 50% of tellurine. And then more percentage of tellurine makes you, the wide band gap is much lower and more metallic kind of transition with like inverse band. Here you can find inverse the band gap band. So the band gap is negative kind of. So this is very good dopant to tune the electrical properties. But I found that when we dope more tellurine rich, these compounds are not stable. Even 2D materials are not stable. Like MOTET, WTET, MOTET, they are not stable. In bulk material form also, the bulk after few days, everything is bulged out and absorbs the moisture. So tellurine rich is not so stable than selenium. So while handling the material, I will keep in the glove box later. If you see the like tellurine is bigger in the size, so that the lattice perimeter decreases as well as the lattice perimeter increases as well as the band gap with tellurine is decreasing. This is
actually get a negative band gap.
Not negative. It's like this inversion they count as negative, right? Yeah.
They define it in some way.
Yeah.
Like an order derivative, and then if it's in one direction, then it has to be negative.
Yeah. This is nice compound to tune. First we tried the DGS method, but in GOTS, now we are trying to buy Chengyong in process to buy zirconia powder. Was just still waiting. He's trying to get some particular size of zirconia powder for the to try in the DGS method. Where has two different types of annealing. We got able to get the single phase of these materials in solid state method. My idea is to prepare these solid state annealing this in cards and then use this powder in DGS method. In DGS method, I would like to, these are the layered compound. Would like to go with slow cooling rates and see it's anisotropic, but you will get more layered and get the anisotropic more transport properties than polycrystalline. So I will also use DGS after doing annealing, or if I able to get the zirconia powder directly, will do the DGS. This is the last time we prepared the samples where this is single crystalline material, where the single crystalline crushed into the polycrystalline. Then he got the XRD in the in XRD. These are our samples are matching with the same phase of zirconium selenide. How to choose it?
Are you doing all of this, or is somebody helping?
Yeah, me and Yuran going to do. I'm getting another master student. Me and Chengyong going to guide two master students.
Okay.
One is zirconium, this one. Another one, another master student assigning bismuth antimony.
Okay.
Me and Chengyong is working on some uncompensated AST as well.
Okay.
Yeah, 3 things, but this is one master student. With master student.
Are these master students thesis masters, or they just?
I didn't check with new guy, but Yuran, you assigned me internship, right?
Yeah.
Yeah, she's helping for sealing and other things,
Yeah.
and also helping for the.
But Yuran is like full time at this point, right?
Yuran is full time. Yeah. Only limited with the SPS and SPS now. Yeah, we get weight. It means these all compounds. I have a list of 10 compounds. Then I will seal and make it ready for the SPS.
So we are hiring one more person for synthesis. Amit Mondal will start sometime.
He's around?
No, he's not. He's still in Kharagpur.
Okay.
So I think by the time.
Oh yeah. We talk to him, right?
Yeah. So I offered him. They will send him an offer soon.
Okay.
Maybe 3 to 4 months till he gets the visa. So
yeah,
I feel like he should actually work on this with Chengyong on the machine learning driven project, but he should have some bandwidth to try other things. So
yeah, happy to discuss any new project, something. Yeah. This I feel like why is worthy. The thermal conductivity is low, and there's so many tuning knobs. This is bulkily not been explored. That here you can tune cation doping as well as anion doping, which we were doing with Jayant, also doing similar way, the tellurium selenium sites. And then zirconia is a mistake. Zirconia deficiency also is a tuning knob. If you how you tune the electrical properties, like zirconia efficiency, they found the conductivity been improved, and they found the superconductivity as well. And the thermal conductivity is not so bad. Like at high temperatures, it can reach. These are the kind of compounds are stable, and then it can reach around 1.
But this is semi-metallic right now?
This is semi-metallic in zirconia telluride. With the telluride.
Transport data for the one where they tuned it so that you actually have inverted band where it's not less pink, for example?
We have.
This resistivity is quite good, right? It is very high.
Yeah, very high. We have. I will show you. But unfortunately, I didn't able to measure the remaining compounds. We have prepared, but they are bulged out.
Yeah. I think I haven't necessarily seen anything that disproves the hypothesis that the DJ's grain sizes should be favorable to thermoelectrics. So this may not be that great, because even I think this will be similar to AGSBT2. The grain size will be too small, then your conductivity will be extrinsically limited, not intrinsically limited. So
yeah,
this is what I'm worried about having this. This is a a longer discussion that we should have anyway for the new project. I don't want to do SPS unless I absolutely need to be honest.
Yeah. I mean, if DGS works, it's faster, right? We don't want, that's how our.
So Cheng Wang is thinking a little bit about what is the smallest sample. He's talking to Lindsys, and I think he also reached out to this Juilliard company that has got the handheld CVAC from. I think we're going to try and get some CVAC measurement tool that can measure 2 millimeter samples. And then even if it's not, even the error bar can be 20 microvolt per Kelvin, whatever, doesn't really matter because it's a screening tool. So it doesn't have to be super accurate, but then you're doing, I do not want SPS as part of the workflow.
Got it.
Yeah.
Try to avoid, okay.
Yeah, so think about this because I think SPS changes the microstructure, right?
I mean, in DGS, one way to tune, I mean, most of the components in got form and melted, they are robust enough on density. If some depends on the layered construction, depends on the material, right? If not enough density is coming, you need to have force, which we need to modify on the DGS setup.
On the DGS, but yeah, so that's another, I mean, I think Delvin has talked about a few things, but we see what he can do first. Like, I think one of the things Delvin is definitely trying is a higher temperature. So definitely the material that you use for the tube is different, right?
What I liked in Delvin setup is like you're able to tune the cooling rates, right? For particular, when you want to grain, it's not worked with the AST samples. We didn't get any change in the transport, but definitely it will work in different systems.
Well, I mean, Weber has a hypothesis that is the heating rate that matters, right? So we should see when Cheng Wang is able to present all these together at some point.
Yeah. This is like zircon deficiency. There's another, we do in MOS2, we see the intercalation, right? These materials are able to, without changing any phase, until 50%, like 0.5 of copper, you can able to incorporate. Whereas above 0.5, they found a secondary phase like a copper pure phase above 0.5. So you can intercalate and change the transport, but it's old. I don't like to intercalate, but just I'm presenting. Intercalation not stable. You can, whenever it is irreversible, and when you heat it, it makes alloy and this one. But whereas people reported intercalation, we know this intercalation is possible in this system as well to tune the electrical properties. This is lithium intercalation and copper intercalation. Are you around? Yeah.
Lithium, I mean, we have some experience in intercalation.
I'm just, my point is, you can intercalate here. Later, if I found the compounds, tunable high power factors, what I choose, I don't choose the lithium or copper. I will choose some rare element, few elements, then where you can get the thermal conductivity much lower.
But okay, just be careful also with these materials because the texturing will be important,
Yeah, texture.
SPS is that you can, what Alex did, you can do it in such a way that you enhance the texturing and that gives you anisotropic properties.
Yeah.
Help all this, but it becomes tricky, so I'll be honest, I'm not a big fan of them. Doping control is okay, but the intercalation and stuff are also very isotropy dependent. So choose it carefully. There's a lot you can do. But
yeah. I mean, integration is the last option to tune further.
Yeah.
Even this is compound very interesting. Like not only the anion doping, this hafnium, a small percentage of hafnium changes the nature of zirconium semiconductor to metallic. It's kind of they are very good tuning knobs, like to tune the transport. This is the old data, where we got the sorry, I don't have electrical conductivity. CBEC is like a p-type, then it decreases with the selenium. Is like semi-metallic compound. When it is more semi-metallic, it's like crossover behavior. This is also observed in cation doping with vanadium and molybdenum doping at the zirconium site. Like the band, it depends on the lattice constant variation. So a small strain can change from p-type to n-type. This is like so I'm going to decide the composition less than 1 in less tellurium content, selenium rich side to tune the electrical property. thermoelectric properties rather than higher toluene content. Yeah. Right now, we're able to find the synthesis, but there are different tuning knobs like at the cation side and anion side. We're just limited with the SPS right now. Then, yeah.
So we don't have a single data yet on any of these compounds.
Not really.
Nothing. Synthesis only powder so far.
Yeah. Annual and then just waiting for the SPS. SPS is down for the last 2.5 months.
Right. No, but when the FYP did it, we didn't get any transport data from it.
No, those components I cannot use again.
Okay. Okay.
Sorry. Yeah, but I'll push this. Like measurements are okay, but need to get the samples.
Can you do Shubiknikov-DeHaas oscillations
at low temperature?
At ppms?
No, it depends on sample. What temperatures? Like we can 4. Yes, a magnetic field is only 9
We
Teslas.
can do very low temperature because I think it's more for. I mean, I was thinking like one of the things that we need to do. Again, this is not for this particular project, but in general, like for screening of thermoelectric materials, right? CBAC is doping.
Yeah.
Right? And CBAC, only if you know the band structure, then you can calculate doping level, etc. That's the traditional theory, right?
Yeah.
But actually, if you think about it, what makes a good thermoelectric material? All this band convergence, etc., is the fancy word for it, but really is the Fermi surface area.
I mean, asymmetry along with the Fermi surface area.
Asymmetry is for CBAC, that's right. But Fermi surface area is already pretty good, right? At the Fermi level, if it has a large Fermi surface, typically it should have a large CBAC. Asymmetry comes from that too, right? So I think one way to directly measure that is like doing SDH measurements in there's some theory. I don't remember it exactly.
Okay, I will check. I never heard, but
I think it gives you effective mass, right?
It gives you I think there's a direct relation through Onsarter that gives you like the Fermi section cross area in the reciprocal space. Okay, I don't remember this, man. This is like a long time ago.
Yeah, it's a solid state physics.
Yeah. So it's called Shubiknikov-DeHaas oscillations. Right?
Yeah, I think it's related with effective mass also, right?
Yeah. So I think it's interesting because say you make a material, have a simple hall bar geometry, you synthesize the material, small sample is okay, you put it in your ETO. And if the hall bar geometry works, Van der Pol or something, and then do SDH, that might tell you directly and then we calculate the Fermi surface. And I think there's some creative thinking, right? It's not the same old and same old.
But particularly, not bulk, thin films or some small flakes. Yes.
No, I mean, it doesn't matter, right? Like the geometry. So you don't need to have thin film. You just need to have the right geometry.
I will check some literature and then do.
Yeah. If you can think a little bit about this.
The associations, yeah.
I think actually, most of the time, if I remember, it's for single crystals. Because I don't know what effect that has on a polycrystalline sample.
Yeah, I think single crystal, yeah.
Usually it's single crystal because, you need to have the coherent. But it's single crystal is a phrase, right? So like if you put a magnetic field and there's what's that called? Landau levels or something.
Splitting of the levels.
Yeah, splitting the Landau levels. That gives you your SDH. Something like this. But
I will check. I didn't.
Time ago, so I need to rethink a little bit about it. But the idea is that the tools that we have, can we use that to be as a screening tool for some new compound, right? So apart from direct CBAC, can we use these sort of measurements that give us a handle on the band structure itself rather than transport, you see? That's what I'm trying to say.
I mean, it's low temperature. Always measurement is low temperature.
Band structure, you don't care, right?
Yeah.
I don't care. Just room temperature is sufficient. You don't even know you need to go to low temperature. You can go low temperature, you get even cleaner signal. Even better because you're probing the band structure. It's better than DFT. Okay, it's not better, but it gives you information that's akin to DFT.
Yeah. We'll think on this direction. We'll see.
I think time to go a bit deeper. Okay, this is what I'm trying to say.
Yeah.
In general, we've built all this knowledge. We are physicists, right? So now we have done some synthesis work. Let's go back to our physics. let's drive this project, not with just new material. We can then, how do you pick a material then? I have 100 possibilities, you know? So the key would be, like, we would probably try to do a few reagents together, just in the binary phase, like say, and then doping. So it already becomes 3 or 4 element combinations. And then let's try to make some materials that then what do we screen for? Like, it could be CBAC, but then that depends on the doping level. But how do you measure the band structure? Okay, that's hard. You have to do RPES, which is why I was thinking this. I remember this from a long time ago. If you do SDH, then maybe it gives you the Fermi surface directly, and that might be interesting. So something like this. So this is, I think, what we.
I mean, I don't know. I got now the point. Yeah. So I will look into that. Okay. No, correct.
Okay, Pawan, you want to go quick? I mean, there's.
Yeah, I'll go quick. I have only 6-7 slides.
That is not quick for sure.
No, I'll just showing the data only.
Oh, that's even slower.
Okay.
No, go ahead. I'm joking.
Can you see the slides?
Yeah. Oh, this is the one with Rob Simpson.
Rob Simpson, yeah. I'm not presenting AGCA. That is 30 slides. I will present in the group meeting.
Okay.
So this is 6 slides. So quickly I'll present. So I've been working on this material from like last 1.5 years. We have a co-sputtered film of germanium telluride and telluride from the Rob Simpson group. So they do sputtering. So they're growing a film for us on the 4-inch quartz wafer. So they have 2 targets, xanthium telluride and germanium telluride, and they co-sputtered on the quartz surface for us. So we have about, this wafer has about 16 samples with the different ratio of germanium telluride and anti-telluride. So, and the value here you see is the thickness of each of the circle. The circle is the one composition of the film. So once we have done, we perform the XRD of these films, and I don't have the full retrieval analysis, but initial stage showed that when you co-sputtered these films, we somehow stabilizing the cubic germanium telluride here at room temperature. Instead of going at 400 degrees Celsius, we can get the germanium telluride cubic phase, because we see a single peak around 42 degree here. Then we have performed the XRF to see the composition of each circle. So, sorry. So each circle we have observed the compositions. Once we get the composition, we have measured the key property with the ratios. So all samples were measured in the M3 from until 300 Celsius. So
you cut them later, is it?
I not cut them. I used the specific. So I put 2 samples here. One is circle, and I also put in the parallel one rectangular quartz substrate also.
It's stuck on top. So
yes, so you have 2 samples, circle as well as rectangle sample here.
Okay.
So I directly put them in the Zen3 for measurement.
What is the substrate?
Quartz substrate only. We have standard quartz substrate for Zen3 also. It's a rectangular 15 by 4 mm. So you can directly deposit the film and directly put in the Zen3. So as a different ratio of germanium and antimony atomic percent, we measure the T properties of 16 samples. And we can see that particular ratio of germanium, antimony and tellurium gives you the pop factor close to 1 milliwatt. It's still 4 times slower than the bulk samples. Yeah. But it's due to grain size, I think because of the grain size is smaller here, so we have less pop factor, but that helps to decrease the thermal conductivity as well. So we measure thermal conductivity using the bridge method from the Sunni group. Yeah, Sunni group. So they help us to measure so we choose only 4 samples which shows the highest pop factor, closest one. And we measure using the bridge method, and the thermal conductivity is quite lower compared to the bulk samples. Generally, germanium telluride is about 4 to 8 at the room temperature. We're reaching around 1.4, and it drops as increasing temperature. So we have at high temperature, 300 degrees Celsius, we're reaching about 0.6 to 0.8. And we convert that to ZT with the value of ZT have achieved is 0.8, which is half of the bulk sample at this temperature. Then we have done some analysis that why we have this enhancement in the properties. So we plot the Pisarenko plot first. We measure the Hall measurement of the samples at room temperatures. As we see that the value which gives you highest ZT has highest effective mass. Somehow this antimony is improving the effective mass of system, which has been reported also in literature. We done the Zonker's plot as well to see whether the sigma input is improved, which is also observed.
Why does one sample sit so far away?
No, there's 16 samples here.
No, in the Zonker plot, the stars.
This is the sample at first sample. The rest samples is here in that region. I just plotted the Zonker at different sigma nodes. So this sample was shitty somehow. But once you introduce more and more antimony and telluride, then the curve shifts. Then the values of sigma node increased. So the highest perfector has the highest sigma node, which is and ZT also. And we also checked the doping. It seems like still overdope. It should be like negative value of beta or higher dope for the optimal dopings. But yep. And similarly,
Are you grain size limited here?
Or grain size limited is a sigma node here. Supposed to be like close to 4,000 the bulk sample.
I see.
Few hundred, I think at least few thousand. But we have like 1/3, 1/4 here.
Okay.
If I can put the bulk data also if you want in the paper actually. It's just analysis I finished yet.
Yeah.
But yes, so whichever has the lowest theta which is closest to the optimal doping has the highest ZT value. So the green which is the sample, I think S12. Oh, sorry. Yep. That's all.
Yeah, it's very hard somehow, even though we try CombiDep and we were hoping for a surprise in a way, right? What does antimatter do? Even in the cubic phase, you still get. But 0.8 at 300 Kelvin is not, this 300 Celsius.
Celsius, degree, 300 Celsius.
Much smaller than what you have with the cubic.
Yeah, compared to bulk, is still half. But I think it's also matter if you can control the doping because Seebeck is like, you see, it's 30, 40, 50 range. Maximum is rating for this sample is close to 100. I want to reach it at least 200 here. Then yes.
Do they have a way of doing that?
I think the more interesting is to if they somehow put more sulfur in germanium telluride because germanium telluride is metallic here. Or they introduce some kind of vacancy in germanium something so that these numbers can be improved.
But I think we don't have any more samples, right?
Because they have standards target actually, unless they make the target with different germanium vacancies, yes, or extra germanium, yes.
There's nothing crazy here, right?
Yeah, nothing crazy here, yeah. But only thing is, we have to show some analysis.
No. I mean, people don't do thin film CombiDep necessarily and with thermoelectrics.
Correct. At this point, yes.
Hopefully you can send it to ACS Nano.
Yeah, we'll see. I just need to finish few more. So first answer, we need to give this how the antimony telluride is stabilizing the germanium telluride cubic phase. So Rob and Kalisha is doing that part actually.
Okay.
So we will have solved this manuscript ready for your review.
Yeah, sounds good.
Okay, thanks.
Cool. Nice. This nice, careful work. I mean, all the data is coming in nicely. I think you followed up with Sunmi. Clearly, you can do thin film measurements now on a substrate.
Yeah, so nice. if she can do, we can try to do more hybrid stuff with them.
Yeah,
actually.
you'll be able to do more hybrid stuff.
Yes, hybrid part I'm thinking to continue with them actually for thermal conductivity.
She can do all that for you, no problem.
Yeah, because we still have some issue with the thermal conductivity. So if they can do.
Yeah.
Yep.
Great.
Okay, thank you.
All right. Nothing else. I think quite nice meeting.
Kedar, very quickly, do you, just following up about the Nature Reviews materials, do you want me to work on it? Am I the bottleneck? Is what I'm trying to ask.
I haven't read it yet.
Okay.
I'm
okay.
Back from my holiday and I had things to do last week.
No, I understand. I just didn't know if I was the problem.
No, I think I will just take a look and I'll finalize and send it back. Unless it's something I need, I'll ask you and Hyman to help with that. But hopefully soon. And TN cannot be included, even he's interested. He cannot do it because Microsoft Research, it's a very long policy of papers, whatever. With GERD, I'll basically say, look, this is it. If you want to be part of this, we can add you and you can provide a comments later. If not, just say no and we'll just proceed. So I'll ask him.
So I asked him in person. He said yes, send it to me.
Oh, okay.
But I sent it to him and he never responded.
But did he say yes, send it to me, like yes, I want to be part of this, or yes, send it to me, I'll think about it? Just do the
yes. He said yes, sure, send it to me and I'll take a look.
That does, unfortunately, that doesn't mean yes, I want to be part of this.
Yes doesn't mean yes. Okay, sorry. I might have misread that interaction.
I'll send him another email.
He's
already moved, right? They've already moved.
He's not in Berkeley. He's in Sweden, by the way.
Oh, I think he's going to go to New York soon after.
He's going in September, I think.
Okay.
So soon, yeah, soon.
Okay. So, all right, I'll send him an email and see what he says. Okay, folks, thank you. See you at the group meeting today. Bye-bye.